Hello everyone, and welcome to the presentation on our paper named The Fidelity of Global Surrogates in Explainable Machine Learning. Today, I want to talk about three things. First, I want to give a short introduction to explainable AI and global surrogates. Then I'll go over the experiments and results, and finally the conclusion and discussion. So first, an introduction to the research of my paper. In explainable AI, we can make a distinction between three groups who often benefit from explanations of machine learning models: the user of a model, creators of a model, and the subjects of a model. Depending on the use case, these groups need different kinds of explainability techniques. One distinction we can make is between global and local explainability techniques. Global explainability techniques try to explain the whole model, while local explainability techniques try to explain individual model decisions. In our paper, we focus on global explainability, so trying to explain the whole model. One global explainability technique that has recently gained in popularity is called global surrogates. In global surrogates, we make a distinction between black box models and white box models, where white boxes are easier to interpret and black boxes are harder to interpret. But black boxes generally produce more accurate predictions than white boxes. In global surrogates, we make use of these properties by training an interpretable white box model on a black box model, and the black box model will be used to make decisions, while the white box offers explanations. These global surrogates have been mentioned in the literature as well-suited explainability techniques, or as a well-suited explainability technique. However, the fidelity of the explanations produced by global surrogates is a potential weakness and hasn't received a lot of attention as of yet. It isn't clear if the white box does indeed correctly reflect the decision process of the black box. This is why in this paper, we research the fidelity of surrogates. In the first part of our research, we try to find out which metric is most appropriate to measure the fidelity of surrogates. In the second part of our research, we use that fidelity metric to look into how high the fidelity of surrogates is, and also to see if certain types of surrogate models have higher fidelity relative to certain classes of black boxes. Finally, we should expect there to be a trade-off between the fidelity and interpretability of the surrogates. This is why we look into the interpretability of the surrogates in the third part of our research. So let's take a look at the experiments and the results. In the first experiment, we tried to examine which machine learning metric is most suitable to measure the fidelity of surrogates. There's a big amount of metrics available out there to compare the predictions of the surrogate to those of the original model. We look at both binary classification metrics, but also continuous regression metrics, which can both be used to measure the fidelity of surrogates. Additionally, we also make a distinction between distance and correlation-based metrics. This way, we end up with a set of 6 metrics, including both discrete and continuous metrics, and both distance and correlation-based metrics. To in some way assert which surrogate is truly most similar to its black box, we introduce 2 additional measures: a permutation importance similarity measure and an accumulated local effects similarity measure. These measures are used to compare the feature importances and the feature relationships of the surrogates to those of the original models. The idea is that the more similar the permutation importance plots and the accumulated local effect plots of a surrogate are to those of the black box, the higher the fidelity of the surrogate is. We applied these metrics to 2 black boxes and 2 white boxes each, resulting in a total of 4 surrogates to compare. These models were trained on 15 variations of generated binary classification datasets. The last column in this table shows the classification difficulty for each dataset as the average accuracy of the best performing black box model. Every classification score represents one data generation configuration. We generate data of 4 different types of shapes, for each of which a 2D example is shown on the right side of the slide. By training the models on these datasets, we in the end produce this table, where we show the fraction of times the metrics agree with one another over the 15 datasets. As shown at the bottom, Spearman correlation agrees most often with the PMI and IL measures. And since we chose to see the PMI and IL measures as the most reliable indicators of truth in this setting, we conclude that Spearman correlation is the most appropriate metric to use. So now that we've determined which metric to use, we can start to look into the fidelity of surrogates. To do this, we again use the 15 generated datasets of experiment 1 and additionally also 5 real binary classification datasets. We made sure these real datasets have varying amounts of instances and features. On both of the generated and the real datasets, we train 5 different black box models, and as surrogates, we train 5 white box surrogate models on each of the 5 black box models, leading to a total of 25 surrogates. For each combination of surrogate and black box, we measure the Spearman correlation on all 20 datasets that were used. From the results of this experiment, we produce this plot, where the average Spearman correlations of the surrogates are shown on the y-axis, all the 25 white box black box combinations are shown on the x-axis, and the error bars are for the 95% certainty interval. Clearly, the best surrogate varies depending on the black box. For random forest and XGBoost, which are the first two on the left, rule fit appears to be the best performing surrogate, but for AdaBoost, support vector machines, and neural networks, which are the 3 black boxes on the right, logistic rule regression performs best. This finally brings us to the third part of the experiments, the interpretability of surrogates. Here we again use the same black boxes and white boxes as in part 2. And as dataset, we use the real datasets from experiment 2. To quantify the interpretability of the surrogates, we use a method from a paper by Molnar. Molnar's interpretability score combines 3 factors into a single measure, where 0 means low relative interpretability and 3 means high relative interpretability. Using this method, we come to the scores shown in this plot. On the y-axis, we see the average interpretability score over the 5 real datasets that were used. And on the x-axis, we again have all 25 surrogates. On random forest, XGBoost and AdaBoost, so the left 3 black boxes, decision trees are the most interpretable. And on support vector machines and neural networks, so the 2 black boxes on the right, rule fit shows slightly higher interpretability. That finally brings us to the conclusion and discussion. Let's first summarize our answers to our research questions. In the first part, we show that Spearman correlation appears to be the best metric to measure the fidelity of surrogates. For the measure the fidelity of surrogates, we see that in general, the rule ensembles named rule fit and logistic rule regression perform best. We also see that the best performing surrogate depends quite heavily on the type of black box. For example, on random forest, decision trees perform particularly well, while on neural networks, logistic regression does relatively well. To answer the research questions in part 3, we can now plot the fidelity interpretability trade-off for the surrogates. We created 5 fidelity interpretability plots, 1 plot for every black box. The fidelity is plotted on the x-axis, while the interpretability is plotted on the y-axis. As we can see, for random forests, so in the top left, decision trees are a clear winner. For the other black boxes, decision trees, rule fit, and logistic rule regression all perform well, with rule fit performing especially well on the last 2 plots, so support vector machines and neural networks. We see 3 main directions of future work for this paper. Firstly, the main focus of this paper is on balanced binary classification datasets. Also, the datasets used in this paper contain 2,000 features at max. While we think most of the results in this paper will hold for other types of datasets and datasets with more features, researching this would still be an important extension on the work of this paper. Secondly, we train the surrogates in this paper in a standard way, which is to simply train the surrogates on the outcomes of the original model. However, many alternative surrogate training methods exist, and we think there might definitely be better surrogate training methods out there. To conclude, we think there are 2 main takeaways from the research in this paper. Firstly, the results in this paper show that in most cases, the Spearman correlation of at least 0.9 is reached, which translates to an area under the curve of at least 0.99. We would say that these levels of fidelity are sufficient for most use cases. However, in cases where truly a great deal depends on the quality of explanations, like healthcare, more sophisticated explainability methods should be used. Finally, we think the research in this paper shows that global surrogates are a practical way to explain black boxes. As long as appropriate surrogate models are selected, the fidelity of surrogates shouldn't be a problem, making global surrogates a potent tool for data scientists and researchers. Thank you for your time and attention. Are there any questions?